Oh, very nice. Wow. Thanks. Okay, thanks a lot, Mateus. Thanks for the organizers. So, exactly. So, maybe I would like to first start with connections Latin America of this project. So it started in Concepcion, in Chile. I know in Latin America there are many cities called that name, so it's about Chile. And as you can see here on the author list, basically like only me, I'm not from Concepcion. So these guys, they started this project maybe even 2 years ago. I had the pleasure to join them also in Latin America, in Argentina, during Quantum Office 7. It was already more than 2 years ago, so the project developed slowly because, as you can see, it's many times some sort of fishing in the dark, but actually we are converging to the final result we wanted to achieve. To show another connection with like Latin America, particularly with Brazil, paraconstant probability theory is based on so-called paraconstant logic. This was designed in Brazil by Newton da Costa. So the project, which started like this 3 years ago, was initially motivated like because of quantum tomography with SIG POVMs and mutual bias basis. So what they in Concepcion wanted to do was to have a probabilistic description of tomography which would be somehow better fitted to this example. What happens at the end is, of course we have this, but we have something else, and I'm particularly very excited about this something else. So let me first start with some basic background what we will use. This is purely like standard logic, so there is nothing new. But the new idea is that from logic, one can derive probability theory. This was done by James 50 or 60 years ago. So to fix the notation, we have logical propositions like capital letters. We have their negations, as in standard logic with the bar. Because it's Bayesian, we have some a priori information. Now you don't need to pay attention on this symbol. It's here because we need it somehow, but it's not so crucial. And we have standard logical operations, so connectors and other implications. And what you use many times in this conference, there are rules like the product rule. When you have the conjunction of two propositions, you can split it into different ways symmetrically. Of course, there is the sum rule, so probability of something and its negation, it sums up to 1. That's like in kindergarten. But the idea behind this book was that when you have the logic, you can build probability theory. Like mathematically, it's highly non-trivial, but you can do this. So why not to test another logic, build probability theory out of it, and see like how much we can go and what we can get. To people interested in quantum logic, this is not quantum logic. This is something completely different, but to be sure that this is the case, I opened this original paper by von Neumann and went exactly to the end when it's explained what the difference is. So mathematically, for mathematicians, like they know that negation is some logical property which is somehow mathematically the weakest one. So if you would like to play with the logic, maybe negation is the good candidate. Well, what they had that time was not the negation, but some conjunctions, disjunctions because of Heisenberg uncertainty principle. So it was completely different. But what we follow is exactly what von Neumann presented here as the mathematical thinking about logic. So we touched the negation. Actually, at the beginning, not we, but the formalism was already there. Constant logic. So what is it? It is as close as possible to the standard logic. So it has all the connectors, implications as normal. Many of axioms of standard logic are there as well. There are a few modifications. Probably the most important one is this. So double negation is not the same as the proposition, but there is something. That's maybe a good explanation at the beginning. Maybe it's even good to see for this line for a moment. In standard logic, whenever you have two propositions or sentences and one implies the other and the other way around, then if you go to negations, it is preserved. You can say the same thing then. They also negations imply each other. So maybe the message for you now is that here it's not the case. even if you have two propositions which imply each other, for the negations it doesn't need to be the case. It's because the negation is somehow released. So we have some freedom to specify it, not complete, but that's why it doesn't hold. We need more two objects which are new and show how this logic is constructed step by step. There is something which is called non-contradictoriness. You take the proposition, its negation, negate it again, and you have something which is always trivially true in classical standard logic. It must be true. But now this is another degree of freedom which can be true if you go to the classical limit, but doesn't need to, and somehow is related to the other ingredients. The second one is, it's called non-contradictory part of a proposition. What you do, you take the proposition, A, and its non-contradictoriness. So again, if the second guy is always true, you are in standard logic. But if it's not, this is some sort of standard part of non-standard thing, I would say. And this is all about this logic you need to know to go further. Actually, this mathematical part I would like to make as short as possible. So I would like to provide you few relations which look like rather trivially. They are very hard if you want to prove them rigorously and check many cases and be sure that it works that way. But they look very trivially. So what happens here is that the probability of a proposition now is simply the sum of the probability of its non-contradictory part, and you have additional ingredient with probability of its contradictoriness. So the negation of non-contradictoriness. So in standard case, this is 0 and this is the same. The second relation is that the negation is not completely free, but is related to exactly non-contradictory parts. So they form like this complete couple. Non-contradictory part plus negation, they sum up to 1. What immediately implies that normal proposition plus the negation doesn't need to sum up to 1, but has this additional term which can contain some information. Okay, this is the formalism really like in a nutshell. So I can't describe more how it goes, how it's proven. There is functional analysis inside, unfortunately, but I believe it's not so crucial now to understand it. What I would like to say is that this formalism, since this is mathematics, somehow I hope it can be like applied everywhere. Maybe in high energy physics as well. Why not? Everywhere people have data, and in this data there might be something which can be explained by models based on this, say, theoretical framework. I will be happy to see the applications. But like these days I was also thinking how to explain like to this, say, sub-community. Like, because you can ask, okay, but what does it have to do with us? So I came up with the, say, this similarity when you exchange the currency. Because you have your own currency. Some of you in your groups, you pay in contextuality, other people pay in non-locality, I don't know, if you go to lunch. So what we can do with this formalist, at least want to achieve this, because we can do this somehow and would like to have it like more general, is that you can give us your contextuality and we give you back contradictoriness. So you say we have a system and our system is shown, of course it's non-contradictory, but it's shown to be contextual. Then we can provide a model which is non-contextual, but it can't go without the price. It must come something else, and this else is contradictory, so it's contradictory. So that's maybe the way of thinking I would like to ask you to keep in mind while seeing the contextuality example. This is only an example. Maybe it's even not the most general case you can get. Of course, like contextuality is a huge topic. This is very good for us because it used the 6 POVMs we had in the motivation, so it can be done very naturally that way. Okay, there is like few like things I need to explain now. So I hope some of you know what 6 POVMs are, but to those who don't know that they are simply projectors, and they are, say, over-complete in the way that they do not sum to identity, but d times the identity, and their overlap is constant. It's like mutually unbiased basis, but different. That's maybe a good description. So what we have the SIG POVMs, and in D dimension we can also have, in some cases, D plus 1 mutually unbiased basis. Now we focus exactly on this contextuality example, so we have D equal 3, 9 SIG POVMs, 4 mutually unbiased bases. This is actually like a fancy geometry, but probably we have no time to discuss the geometry behind that, like, deeper. And now what we can do with this situation? We can say we have 9 projectors for SIG POVMs, and we say we associate 9 logical propositions. Up to now, we say nothing about them. We only say that they have to correspond somehow, one by one. And what we will study is the sum. So we take the probability of each proposition and we sum them up from 1 to 9. And we would like to see what happens. So in quantum mechanics, it's easily done because what the probability can be. Everyone will say, for sure it's the projector, which is associated with some mixed state, which is already there, the trace, and we have it. If we say we proceed like that, then the value is always equal to 3 independently of the state. That was the result from the paper we are using. Okay, so 3 is the quantum value. And now what happens if we do not want to discuss it like in a more quantum way? The idea like behind this fancy geometry is that, okay, you have 9 SIG POVMs, so you have 9 propositions, like they are aligned in this, say, square lattice, and you have 4 mutually unbiased bases. Each basis gives 3 lines. And the geometry is so nice that in every case, so these are first basis, second basis, third and fourth mutually unbiased bases. In each basis, it's known for sure that 3 SIG POVMs will be orthogonal to some members of this basis. For sure 3. So if you are in the first basis, the first 3 will be orthogonal. The second basis, other 3, so in total 5, because in this non-contextual scenario, you would like to sum up this information, not to miss it. This is actually like only one example, probably like all configurations, there are 27 or maybe more, but I call it generic because it contains all I wanted and I want to say, and in other cases there are only permutations, and maybe it's even 1 dot more, so it's even worse from that perspective. At the end you have 7 dots, and these dots, this means that such propositions, they cannot occur. Because if you want it to be non-contextual, you need to take all this information, and each part says about some of them that they can't occur. When you take all these bases, 7 of them, they can't occur. And what does it mean? This means that the negation of this 7, this is true. Simply it's true, and that's all. We can't play with that, but we can see what does it imply. Of course, it implies that probability of each negation is equal to 1. That's true. But now comes the new thing. So when we are still in the standard theory, we already fixed 7 probabilities to be equal to 0. There is no other choice. If we fix it, the sum contains only 2 and is bounded by 2. So we remember in quantum mechanics was 3. This is bounded by 2, and this is the contextuality inequality in this scenario. So when you follow classically and you have this non-contextuality, you need to have the bound of 2. And now comes the situation, what happens in this, say, new framework. Again, we have constraints for negations, but now because of this relation, they only imply constraints for non-contradictory parts, so for this degrees of freedom which are, say, standard, classical. And when we expand the sum, of course, we have these 2 terms which are still there, but we have like huge freedom present. So the bound is still 9. There is no constraint, actually. We plugged non-contextual information as it was, and still there is nothing new, like the bound is 9 as it was at the beginning. Like this is a sort of small digression. Once, like I attended the seminar by a mathematician, and he like discussed some operator algebra, so on, and he wrote down this uncertainty relation. Suddenly he said, but look, I don't want you to think about this as Planck constant. Then someone immediately asked, okay, so how do you want to call it? Then he replied even quicker, a parameter. That was quite funny and in that context, and this is something which happens the same here. So people could like have in mind, probably he tries to present another way of quantum mechanics, maybe, or something like that. So no. How I would like to call this theory and this all results, this is simply like a framework, which I hope is useful. This is not quantum mechanics. This is a framework which can accommodate many, like some amount of information, so potentially more than quantum mechanics, and can be applied to other fields as well. Okay? So now what I will do, some of you can think, maybe there is now fine-tuning coming. What I would like you to think about that is not fine-tuning, but that we really would like to use this idea of exchange, like currency, and design some exchange rate. Because if we have the framework which is too general and can be applied to anything, we would like to see if it can really provide also particular models. So now, for instance, this quantum mechanical value. In a way which is not completely stupid, but makes some sense. And to do this, we have two steps. The first step, and physically this is very nice actually. So of course we know like being non-contextual, we took the information from all 4 bases we had in our set. But in practice, when we do like some experiment, we have 1 basis at a time. We don't use 4 immediately. So there are measurements which are performed, and there are some other which are unperformed. And still, because we wanted to have non-contextuality, if they are performed or not performed, we still know that the dots need to be black. The only question is, if there are some measurements which are not performed, do we know for sure everything about like these propositions which are hidden behind that? And exactly, so if we measure, say, the first basis, because that's what we fixed for a moment to make some reference frame. If we measure the first basis, these 3, which were known not to occur, this is somehow is for sure. There is no contradiction because we have access to that, people can measure it, there is nothing weird happening. There is no way to say, there is something contradictory happening. But always there is the rest. There is the rest of objects about which we can't say like with so huge certainty. So we still keep this fact that they do not occur. But maybe there is some contradictory behavior, so maybe they occur and do not occur. Like this weird stuff I want to sell you. And then what happens if we include this? So this is the first step. We include this information, so we took the first basis, so some of degrees of freedom are non-contradictory. So in that term, in that way we cancel some of the degrees of freedom because we say, okay, for these 3 which are associated with this first basis, we know there is no contradictoriness. These 3 go out. Still we have 6 terms here, and still we have the big bound 6 because the model is still too general because it can accommodate more information. If we would like to go down to the value you might find desired, we need to do another thing. What we can use is that our CPO VMs, they have this symmetry. So in dimension 3, they all overlap with 1/4. So what I'm doing now, I really wouldn't like to call it fine-tuning because it's trying to find if the model can accommodate some like additional features of the system. And if we, and exactly, what is contradictoriness actually in this case? Because this is a crazy word which appears here all the time. So in this particular model, we can clearly see that this is somehow the same as non-orthogonality. If some objects are non-orthogonal in quantum mechanics, then even like in a single shot experiment, you can't determine exactly. Then also like when you use them, there might be some contradiction. Like one is not because you found one, but because of non-orthogonality. So if we use non-orthogonality to go further, since this value is always the same, it's fixed for CPOVMs, we can take that with a very simple model that all these 6 degrees of freedom, or maybe their inversions because there is no bar, they are equal to some constant value. There is no difference if we think about number 5 or number 7 because of the symmetry hidden in the problem. And if we include this particular information and use the fact that, for instance, non-contradictory part is always less probable than the non-contradictoriness itself, it must be like that. Then we go back to the inequality which contains this parameter, and this parameter can nicely interpolate between all these cases we could have. First, there is no contradictoriness, so this parameter Q must be equal to 1. This bound is 2 again, so this is exactly this limit of standard situation. On the other hand, we can say maybe there is like full contradictoriness. Maybe all the projectors which are not measured at a time, they have this huge overlap between them. Then the bound is 6, and we can do nothing with that. But if we would like to say, okay, if contradictoriness is non-orthogonality, and we know how much non-orthogonal these projectors are, and if we plug the value to reverse, so it's 1 minus 1/4, exactly how it comes, then the bound is exactly 3 as in quantum mechanics. And again, I need to say, I would like to tell you what is the purpose of that whole game. It is at the beginning, like in this contextuality scenario, of course, like there was no contradiction because that's how it used to work. But contextuality was necessary because the bound was like the value was 3, and the non-contextuality bound was 2. So contextuality was there. One can even say, okay, we can maybe somehow measure it, saying how big is the violation of the inequality. Okay. In this framework, we have the model which is completely non-contextual. All the information of contextuality is accommodated properly. There is no issue with that, non-contextual completely. But there was a price to be paid to be non-contextual and still describe the value given by quantum mechanics. And this price is that we had to exchange contextuality into contradictoriness. So contradictoriness, so something which describes non-orthogonality of projectors which are not measured actually. They are there in the description, but they are not physically like played with at the moment. And in principle, so this is a mathematical framework. So I'm hoping it can be applied also to other things, to other, say, resources, to other quantum features which go beyond standard probability description. Probably in many cases it's possible to say, okay, we can get rid of some of them and try to explain in terms of contradictoriness. The question how much this new description gives us, that it's for me it's open. At least for me it's striking and I find it interesting. I hope it will develop well. I hope it will also go beyond like this scenario, I would say. So if anyone would like to know more about it, because we need to have the draft very soon, but it goes slow because of some mathematical difficulties, I'm happy to discuss, and maybe someone would like to see how this situation works in the particular scenario under discussion. Okay. Actually, apparently I'm the last speaker who is not the organizer, so I was also appointed to thank our three. Yeah, I was appointed to thank our great. Okay. Okay. Okay, so thank you very much. I think all of that, we are very happy that we are here. We could be here the whole week. Like, I enjoyed it very much. I've seen many people enjoying like everything, like parties, enjoying talks, enjoying dinner, enjoying beach, like enjoying this institute, which is actually like really awesome. So thanks for organizing. Thank you, Raphael. You did it here. Yeah. If anyone would like to say something, I can only invite.